one way to present a cell, to present protein function. Protein function, again, there are different types of functions. Some of those related to subcellular localization. The most important background problem is we have a lot of sequences, not for a lot we know function. When we predict subcellular localization, there are different methods we can use. One is essentially using sequence similarity, homology-based inference, where we have a protein K, for which we know the subcellular localization, protein query Q, for which we don't know the subcellular localization. If these two have a substantial amount of sequence similarity, so this should be larger than T, of course, here. The percentage sequence identity between the two is larger than some threshold. We can infer that Q has the same localization as K, and we have established this. Here's the blue curve for subcellular localization using H-val, the H is a p-distance, using the blast E-value, or log of the blast E-value. We can see that at least for some set of pairs, as long as they are somewhere substantially above this blue curve here, the inference is above, say, 90%. For something H-val plus 10, it's about 90% for something like H-val plus 30, roughly. So in this run, homology-based inference works. There was this brief presentation of text similarity, the case where I do have some functional descriptors available for my protein. Although I do not have the descriptor for subcellular localization, I can simply grind up all these keywords here into a database, the meaningful, for this classification problem, meaningful keywords as a vector written here, of which I see 1, 2, 3, 4 components, and so there are many hundreds of them. The rows are the proteins. That creates a vector where a keyword is not there, is there, not there, there. And then essentially I will use this keyword in subvectors in a database, and I simply look up what is the closest of proteins for which I know the subcellular localization, for which I know the keywords, to the query protein for which I only know the keywords. Then there are motifs. Motif is another sort of, it is related to homology-based inference, but now we no longer really mean homology. And the reason for that is we no longer require that these two proteins are really similar in sequence, that we can make any inference about their relatedness in evolution. But what we do see is a motif, a local region, something that is relatively short in sequence and is meaningful. There are two different types of motifs. One is sort of sequential, meaning that when you have the stretched out chain, you can recognize the motif. Another one, conformational, is such that on the linear chain, you will not find this motif as outstandingly significant, but when it folds into a three-dimensional structure, you see the motif. I have told you that there is the type of motifs such as the nuclear localization signals that are spread out over the sequence. Spread out means you can find it anywhere in the protein. They have very different lengths, and what we essentially can only do here is collect all these motifs, build up a database of these motifs, but we cannot do machine learning on those. We can essentially only archive whatever is experimental knowledge out there, and essentially that's the end of it. We can do some refinement. I showed you some ways to refine by simply making sure that the signals that you use are unique for nuclear localization. Then there is the type of motif such as signal peptides, transit peptides, target peptides. You begin by understanding the grammar. With grammar I simply mean, well, they are all at the beginning of the protein. They have a region that is hydrophobic. They have a region that is polar. They have a certain length. That's what I call grammar. So there are some features to these. And you could just have a probabilistic model where you use these features, a Bayesian model for instance, or you could have some more advanced machine learning HMMs where you have local motifs for hydrophobic region, local motif for the polar region, and then you put all of this together in one HMM, and that HMM simply predicts the signal peptide, or transit peptide, or target peptide, or apply a machine learning device. There are different ways of doing that. So this can be machine learned, and it works very well. Now, all the other types of motifs that are there is no solution of these two types. And the reason for why there's no other solution, not even to collect the motifs and build a database kind of solution, because they are all of the type, you need to know something on top. So you need to know that the protein already is on the secretory pathway. And then you see motif that keeps it in the endoplasmic reticulum. It's a retention motif. But you need, if you look at the retention motif in all the proteins, you find many, many, many proteins that are not on the secretory pathway, that are not retained in the ER. The reason is it will only be applied to proteins, or it's meaningful only to proteins that are already on the pathway to the ER, right? And that, for that you need the signal peptide. So many of the others essentially are motif combinations in that sense, right? And again, even when you know that there's a secretory signal peptide, the retention motif is still not accurate enough. You still need to know more. That's why they are not of these two types. Either way, most motifs, most zip codes, so if I imagine the protein to have zip codes that direct where the protein goes, most are not known, okay? And that brings us to motif, text similarity, sequence similarity is not enough. We need de novo predictions. We could predict from structure, and toward this end, what I talked about here is when you just look at the amino acid composition on the surface, you see that the surface compositions here, the logos of the letters differ. So there's 20 amino acids, proportion to how much that they are used in extracellular proteins, cytoplasmic and nuclear, and you see that the three differ. Since the three differ, you can put that into a prediction method. Very simple, but for that what you need to know is the three-dimensional structure. You need to know where the surface residues are. And that brings us to, again, briefly, I had this eigenvector decomposition for nuclear extracellular cytoplasmic proteins that was published in '98. And then just a few years later, Rajesh Nair redid that, and that is here. He used a different color. So nuclear now is green, extracellular is red, and cytoplasmic is black. But what you do see here is, again, I'm sorry for the quality of the slides, but clearly the distinction before was better. The reason is that in this particular slide, well, part of the reason is that in this particular slide, he actually had to predict subcellular solvent accessibility first. So here we are not using structure, but we're using only sequence. We take the sequence, predict which residue is going to be on the surface, use that to compile the composition, and then you see that the separation is no longer that clear. You have some red ones here, extracellular, that sort of fall out. Maybe some nuclear and green that fall out above here, but most are in the cloud. Meaning that yes, there is a clear signal from the surface, but if we have to start with a sequence, we're losing it in the mistake in predicting surface exposure. We also see that for the same data set, the amino acid composition-based separation is even worse than the one I showed you before. And the reason for that now is that there was much, much more data, and it turned out that the story is more complex than it appeared with fewer data. That's as simple as that. There's no reason in the beginning when we did this work, this was about 5 years after the first slide. A lot of proteins had been added, and there was no reason to expect that things would sort of look different in 5 years. But they did. And in fact, this is often the case. Here is a separation of just using secondary structure. I'm also not trying to defend that we have a clear separation of the three types of points, but I want to point out that this is it seems to be not much worse than that. Now the reality is here I have 3 units, here I have 20. So compiling an eigenvector composition here is much more challenging because all I have is HEL. So I have 3 secondary structure segments, and I try to classify according to what fraction is in helix. And that works at all, for me, was very surprising. I'm not saying this is a good separation, but I'm trying to say that there is some signal in here. This is clear, and it's actually surprising that there is. I did not expect it. So what Rajesh then did is sort of he combined these 3 signals as a simple vector. And again, this is clearly no super separation on the first 2 eigenvectors, but it is good enough to sort of begin to see that there is some green, there's some red, and there's some black. So again, we begin to see a separation, and this is linear. This is simple eigenvector decomposition. It's a very trivial method, PCA. in the first 2 dimensions. So when you see something such as this with the PCA, you, again, don't ask me why, but if I see something like this, I believe I would begin to suspect that you can actually learn something here in machine learning. Why do I say that for this one? What would I say here? I believe I would even dare to do it here. When do I look at the PCA and feel that the PCA failed and yet machine learning can fail, and when not? There's no answer to that. The simple answer is I've been wrong. So whatever I answer to that question is not reliable anyway. Let's have a brief insert into the concept of neural networks and SVMs. So the principal idea is you have an input layer, you have an output. In this particular case, you have 2 input units, 1 output unit. You connect the input to the output with a connection, a junction here, and the computation is by multiplying the value of this one, the output of this one here, with a weight that you have with this junction. So you do this times this, plus this times that, so you add, and that essentially is the sum over this vector product. Here's what comes in, and it is in fact a vector product, so you multiply the vector of this with the vector of the connections. Geometrically, this is the interpretation of a vector product, right? You look at the projection, and then, so this is essentially getting into this unit here, and what gets out is you switch with a trigger function. The trigger function here shown is a hyperbolic tangents, could just be a sigmoid, 1 over 1 plus e minus x. Essentially, the idea is the function is such that very high negative values will be switched to 0, very high positive values will be switched to 1, and something that is differentiable in between. Okay? Something you could in fact also have this as a sort of linear approximation in between. People have used that before, and you could use other things. This is just happens to make the computation relatively easy. Sorry for the next slides. So the idea, and I'm just going to zoom through them. So if you want to classify 2 types of points, the way to do it is to change these connections, because that's the free variable, and you change these connections such that the error, so the output is a classification that you try to achieve, so you know the answer that you want. You get an answer from the initial label of the connections, and you try to reduce the error, meaning you try to make as many points fit to what you want as you can by going downhill. Downhill, again, you adjust the connection such that you get less error. What you essentially can do is you classify points by introducing a line. In the simplest language that I showed you, where you have 2 input units and an output unit, essentially you really have lines in a 2-dimensional space. And all of these lines here would suffice, would be right to completely correctly classify dark and open points here. For this case, you cannot have a straight line to distinguish. That line could distinguish, but the language that I showed you so far, the math that I showed you so far, only allows you to have straight lines. So with 1 straight line you cannot do it. You could do it with 2 straight lines. Now, how would you create a second straight line? And that essentially is the idea of the hidden layer. Through introducing a new layer here, hidden layer, that allows you to introduce more lines. Now, lines is strictly speaking only when we have 2 input units. The moment we have more input units, we have higher dimension, and then what we actually have is hyperplanes. So this then allows you to have more hyperplanes. Now, again, this image that 2 hidden units is 2 hyperplanes and 4 hidden units and 4 hyperplanes is too easy. This is unfortunately not as simple. It's just that the complexity of a number of hyperplanes essentially increases. How exactly is more complex. Now, they are called hidden because simply this is the input that sees the world, that's the output that sees the world, in between is only computation. The way the computation is done is the same as before. So initially you multiply this with a connection, that's the input here, you have a tangent, you have a sigmoid function, and that comes out. What comes out here is multiplied with this, that is multiplied with that, these are added, sigmoid, the same as before, right? That's essentially shown here. So you multiply the connection with the input value, you sum over all the incoming connections, you apply the sigmoid, and you do the same thing again. Then the error, so that is defining the output. The error is simply the difference between what you have and what you expect. You square it and sum over all output units. In our case, The simple example that I showed you, this is one. The free variables, again, are the connections. And in order to train, what you do is you change the connections. You do it by, in fact, going downhill with respect to the error. Going downhill with respect to the error means you do the derivative of the error with respect to the connections. As simple as that. You do a negative here because you go downhill. Okay? You do an epsilon because for every single time you present an example, you jump a certain distance. So you go not the full downhill move, you jump a little bit to avoid jumping into the wrong direction. And that is essentially is given by this epsilon here. It's the jump width, so to speak. And then you wait for the next example and you jump, and wait for the next example and you jump. And then in this particular example, you would be trapped in a local minimum. You get out from the local minimum by adding another term here. The other term essentially allows you to jump up by alpha using the correction they did in this time step before. So that's a term that allows you to go up again against the downhill move, so up the hill. And now the free parameters in the game, again, the real free parameters are the connections, the number of hidden units, the epsilon, the size of the epsilon, and the size of this alpha, right? Typically this alpha is larger than the epsilon, and typically you make the epsilon, once you know how to solve your problem, you make the epsilon as small as you can. So typically you do it fairly large. Say this is in the ballpark of, say, 0.1, the alpha is 0.3 or 4 or 5 or something like that. Then you find some initial solution, see whether the system can do it at all. And once you know that it sort of works, then you put the epsilon to something 50 or 100 times smaller than that. And the reason then is, by walking slower, you're more likely to find the best point. Okay? So far, so good. And then we get into this issue of overtraining. Can somebody in the room explain that curve to me? Ideally somebody who has not taken last year's course. So ideally somebody who doesn't know the answer. Okay. That's actually what I mean. Can somebody who doesn't know the answer explain it? But I believe this is the kind of question that doesn't get an answer. Okay, so I have a data set. The data set, my assumption is, represents the world. So the data set I have today, I assume is representative of what I'm going to find tomorrow. This is a very, very important assumption. And this is where machine learning very often goes wrong. Because what I have today is biased. Okay? This is why I have to massage my data by kicking out bias as much as I can today. Nevertheless, this is the assumption. Then what I do is I split my data set at least into two data sets. One is used for optimization, for training. That's the green. So what I show here is the training time. Training time means how often I present these samples. What I show here is performance, accuracy. Okay, how many of the points I classify correctly. 100% is completely right. The training goes up. So the more I train, the more I can learn it to the point that I completely can learn it. Okay? This is not the case for all problems. If you cannot learn it very much to the top, what do you do? What can you change in your game? So say, let me first make my point here. And then I get back to that question. The blue one is the holdout, the test set. And that set for me simulates tomorrow's data. So I pretend that I don't know what this data is, what the answer for those data is, what the answer for those data is. And what I see is that for some point of the training, blue and green both go up. And then comes this point where only green goes up and blue saturates and goes down. This is the point that we call overtraining. We call it overtraining because the assumption is that from this point on, all that I learn is to optimize the training set. I no longer learn anything that has general validity. I no longer learn any principle. I know something that is specific to my training set. That's learning by heart. And in this analogy of learning by heart, until this point here is you understand. So you increase your understanding. And from here on, you essentially learn by heart, right? So in the exam, I'd like to somehow test you at this point. I don't want to find out what you learned by heart. Ideally, I'd like to understand what you understood or measure your understanding, and that is very time intensive and very complicated, as much as it's complicated in machine learning to find this point. Now, let me get back to wait a minute. How can I make sure that I'm not overtraining in my machine learning device in this neural network? What do I do? Anybody?
What do you mean by make sure? Find out that you didn't overtrain, or measures that you don't overtrain?
Measures that you don't overtrain.
So use a model with low complexity.
Yes, Gregor, that's a clever answer, but it's an answer above the pay grade. No, you give the right answer, but it's too complex. It's the next step. The first step is, what's the first step? If you see this in your data set, what do?
Take another train set.
Yeah, well, we're getting into Gregor's direction again. But what's the simplest thing you can do? Simpler. Nothing new. You have it already in front of you. Just take it. But how?
Just stop training it.
Yes, you stop. Okay. Both of your answers, Diane and Gregor, were right, and we're getting into them in a moment. But the simplest first measure is stop, right? Now we get into the next issue here. If I said stop because the blue goes down, is that proper? So Gregor says it's not proper. Can somebody explain to me why? Gregor is right, this is not proper. Why?
Because we are using the test set.
So the major point of this split was, I pretend in the holdout set that this is the world of tomorrow, some data I've never seen before. And I can only maintain that view if I never use the data for any optimization. If I decide at which point to stop, then I use it to optimize. Right? I use it for a crucial decision, because if I kept training, I would overtrain. And that would be bad for tomorrow. So it's a very, very crucial decision to stop here. At least in this graph that I show you. So I should never do that, and therefore, in fact, I need threefold split, where I need one data set. I typically refer to it as the cross-training set, but there are many words out there for that. A cross-training set that you use to optimize other aspects of your machine learning device. It could be, when do you stop? There are other issues, and we'll get back to that later. But anyway, so then there would be another red data set that you don't use for anything, so you stop at this point, and then there's another red data set, and you see how the red data set does, and you report essentially 1 point. And if it turns out that you ever looked at a curve like that, you should actually never do that, but if you ever did, and you saw that the red has a different optimal point, then that's what it is. So you will never get to the optimal point, but the true answer still is that point, because that's the point you did decide on without using the red data set. And that's the way you have to do it. Okay, so now I had another question here before. And given what Gregor said, he's not allowed to answer that one. But so what if I could not get to 100% in my training set? What would that imply? What would you learn from that? So no matter how long your training time is, you just don't get to the green 100%. You may say you don't care because you're going to do early stopping anyway. And that may be right. But what could be the reason why you don't reach 100%? There could be several reasons. Can you name some?
I can't separate my data.
Because? Yes, that is correct. Why? What could be the reason?
Some data have same issues or something, and
Could be that there are mistakes in your data. So it could be, indeed, that's a common problem, right? That you have some data that is mislabeled. In fact, we have been hunting for mistakes in the experimental data just this way. We have taken an artificially large neural network and have tried to train, and whatever we couldn't train with a super huge network, we just threw out. And then we tested on the whole data set always, but we left some of it out for training. And in fact, we left exactly out from training what we couldn't distinguish, okay? That's one reason. Another reason, very related, but slightly different, actually nothing to do with the experimental problem. Yeah?
Some parameters are missing.
Yes, so ultimately, while you're completely right, what does it mean for you as a user? What will you change?
You have to look for other parameters to...
What exactly? How do you look for other... I don't have you.
I guess I'm on the picture.
Oh, yes. But you're not named.
Sebastian.
Actually, there are two people not named on my picture. Do you have a pen? Can you get him? There are two whose names are missing. Yeah, Sebastian. But what does it mean? You just answer my question first, and then you write your name.
That I can't observe some...
Yeah, but what will you do? What's the action item? What will you do differently? Some features are not really there, but what does it mean features are not there? Anybody?
In this case, we can introduce another hidden layer.
Yes, now that gets very close to, in some sense, what Gregor said. It could be that the complexity is too high, but it could be something else. It could be, so I misunderstood Sebastian, or misunderstood, I'm not sure. But the way I read the answer from Sebastian is a slightly different direction. It may simply mean that you need to add input units. It may mean that the features, at least that's the way I understood you, the features that you didn't put in is there's input that you could have used and you didn't. For instance, you put in only amino acid composition, but you should also have put in surface or something about a surface. And that would have been able to classify. Yes, there are issues where you have experimental mistakes, but maybe some of the classification didn't work simply because you did not have enough relevant information in the input. And it could be that the addition of hidden units would help it, but it could be that it is a problem at the beginning, right? If the sequence features do not distinguish enough, then you cannot solve the problem, no matter how you blow up the hidden units. So this is unfortunately, you cannot measure that. You cannot look at the overlap of vectors and see which one you can classify and which not. And that ultimately is because there is no way to say, for my given classification problem, the overlap between two proteins or between two vectors is X, and X is relevant. X is only relevant for a certain classification problem. That means you have to see how much it works. So you have to essentially train a machine learning device and try all of these things, blow up the hidden units, and if it were in your network, possibly cut out some examples because they're dirty, and see whether you can classify. If you cannot, blow up your input to some extent. That ultimately is the way to play around, and that's why it is very much of a cooking book recipe. So you play around and you try. Okay, so this is a particular example we showed last semester where we have an input sequence, in this particular case 13 consecutive residues in a protein, and we want to predict in 3 output states whether the residue in the center of this thing here, P, is in a helix strand or other. And for this particular example, now the colors are different. The previously green is here, the red one, that's the training set, and the previously blue is pink here, purple, and you see that now, in fact, yes, there's overtraining, because there is a realm, or there's a part of the training when this goes up, and then comes something where that no longer goes up, there's a saturation. But the overtraining point here is much more difficult to find. And what I've seen in reality, it's very often more like this than the image that I showed you 2 slides ago. this idea that overtraining is like this, and you can easily see it, in reality, usually is not as simple. So in this particular case, you may really ask, is that the best point here because that's the highest point? Is that the best point because at that point you have done less overtraining, or is that actually a better point because some of that what you have learned here is still generalization, otherwise this would have gone down, and because there's still some generalization, at least for some proteins you learn something specific, unclear. Yeah?
If it shows the right model complexity, doesn't it converge at a certain point, and it doesn't really matter how many cycles you run?
Well, let's look at this in the most extreme set. So if you do 0, it doesn't work, right? So it does matter. So you need a minimal. It doesn't. So your statement "it doesn't matter" cannot be right. You need a minimal set.
It doesn't matter to run an arbitrary huge number of cycles.
So if you scale your system right to address the right complexity, then you will essentially run the system until conversion somehow. This again is one of those stories that you would hope that it works that way. In practice, very often not. It is very, very difficult to find these points. And that ultimately, again, the reason why this is more dream than reality is because you apply it exactly when you don't understand your data well enough. And you apply by applying the machine learning, you begin to understand about your data, and then typically, so the last master thesis or PhD thesis in our group is one where we now clearly understand that the data is incredibly complex, and we don't have enough data. So now what? More data we don't have. Bigger model we cannot build. So what I'm trying to say, typically to find such a luxury point where the system converges is unlikely. Okay, just to keep this in mind. Now let's look at the SVM. That comes from Vapnik. It's really completely his idea. And many of the images of SVMs, you begin to see it this way, that you have some classification that is not easy, you project it to a higher dimension, and then suddenly the classification gets easy. That part is the same as the neural network. The neural network does exactly that by the hidden layers that in fact introduce hyperspaces, or by blowing up the input space. It does exactly the same kind of problem. The next issue is where the crucial difference happens. So Vapnik argues, well, there are some points here, red and some green, that are so far from each other that their classification is trivial. Any kind of device could classify them, so let's ignore them. Let's focus on the more complicated, on the more challenging part of the problem. The more challenging part of the problem, the most challenging part of the problem, is simply defined as pick all the points that are red and green that are closest to each other. So the points at the interface. So define some line through the red closest to the green, and through the green closest to the red, and then find the medium between these two lines. That's the support vector that the machine finds. So that then is the best classification point, because it classifies the most difficult to classify points. Okay? And that is a great idea. And that is the unique difference to the neural network that sort of finds an average of all these points. Can you sort of guess some of the advantages of the SVM over the neural network? Right from here, from this concept?
It's faster.
This is because it uses fewer points, so the rationale for your answer, Diane, I suspect is it is faster because it uses fewer points, and that is right. Because you somehow zoom into the most complicated to distinguish points, sometimes it gets slower. But the tendency is indeed it's faster. Yes, that's right. For many problems it's faster. Yes, but that could be crucial. But there's something in some sense even more crucial. So CPU, sometimes you have. For some problems we don't have enough CPU in computational biology, but so let's just put things down, whether an SVM runs a week or it runs a month. If you have to do it once, your thesis takes longer, right? So this is not that long on a scale. Again, there are examples where the numbers are such that they become prohibitive, and this is an argument. But typically there's something else that is a more important argument. Is there something else you see in here? Yeah?
Could it be more accurate because it zooms in?
Yes, that in fact is, that could be the case, but this is not necessarily the case. Yes, in fact, yes, no, full stop, yes. But it's still not the major point I meant. It's often more accurate, that is correct. Yeah?
I think it works better for little data.
You throw away 90% of your data. Turn that around. That means you can essentially survive with only 10% data. So when you have small data sets, the SVM may be the only solution. The neural network needs a lot of data to find its good average over a lot of data. The SVM is essentially geared to living with a small subset of the data. It's just optimized for that. Let's call it this way. And yes, therefore, the SVM is particularly interesting for examples where you have few data points. As in fact, turns out the story of sub-cellular localization is one of those for which the SVM, possibly because of that, has an advantage. But there is now a downside to it. Can you see that one? Think about biology. I mean, think about experimental biology, or think about
How we define closest. So
we're getting in that direction of that where the problem is. Closest is always by your projection. Closest essentially is defined by your input space. So you find the input space is defined by the features you put in, the input units, and then you have a projection through the kernel. And that then defines directly closest. Yes, and somewhere there is the problem. But where?
transferring a biochemical function to just a number we can input.
No, the problem is somewhere else. Look, red, green. I find the green points closest to the red points. Imagine some point we're lying. Imagine some red point saying I'm red, but it's really green. How could that happen? Is that obvious? Or is it too obvious?
There is a mistake in data.
Yes. Experimental mistakes. If you have an experimental mistake, this device will exactly zoom into those. Because those, if I mislabel any of these points, those appear to me immediately be the ones closest to the other space because they are in the wrong space. So they will immediately get into the SVM zoom area. They are somewhere where the space is closest and therefore defined as this is the point in between. So the SVM has a tendency to, if there are errors, to find those errors and use them for classification. And that, of course, is going immediately wrong. So there is a way to get a little bit around that. It has a parameter that allows you to ignore some part of your data. So you can choose this parameter that says ignore 1% or 2% of the data. But you immediately see this sort of as a tricky point, right? Because that may be relevant data, maybe mistaken data is complicated to say. But anyway, so this is the advantage of the neural network. If your data is dirty, the neural network has a classification that is averaging over the data anyway. Outliers don't matter. Here, outliers could be crucial. That is the problem, the strength and the problem of the two. The idea of machine learning, briefly explained through Teresa, is on this issue of how do I optimize that I'm happy when this thing makes a tone in the morning. So maybe sort of I can predict that how many hours I was awake last on the day before, and then I sort of have some data points and I see that this simple model works or it doesn't work. If the simple model here I would somehow make maybe the cut here and would make one mistake. If that is not good enough, maybe I will also look at how many hours I slept before this thing rings. And maybe on these two values or in these two features, I can then find a simple distinction, which is this. And this is exactly all that machine learning is doing. You try to find features, input units, that are relevant to distinguish your problem. And then you project it into a space, in this particular case it's a two-dimensional space where you can immediately see a line, into a space where you have a simple way to distinguish. Okay? That's the entire idea. There's the line here. And the SVM now does a binary classification. So we cannot translate the problem of the SVM generically into one where we have multiple states. We just have two types of states, green and red in this particular example. That's a binary classification. In contrast, the neural network immediately allows you to have any number of output states. So in this particular case, HEL, secondary structure, this is a multi-state classification. How could you machine learn three localization classes? Well, one, of course, is to use three output states in the neural network. And how could you put that into a binary solution? So if I were to try to do that with a neural network that has only two output units, or with an SVM, how could I do this? I have three sub-cellular localizations. How could I classify them?
Like three binary classifiers.
So one that says extracellular versus other, one that says nuclear versus other, and one that says cytoplasmic versus other. Now, the important thing then again is what's the input? So I want to predict sub-cellular localization. So what input should I use? Any idea? So these 3 units is just a symbol there. The number is not necessarily 3. Any idea what you can use to build sub-cellular localization? Well,
We control all the things and
Yeah.
share output.
throw some at me.
Composition.
I mean, as a composition. This would be 20 input units. What else? Yeah?
Secondary structure.
We have seen that on that slide before. That would be 3 input units. So this is the number of input units. Yeah?
Why is it only 3?
Well,
Like the majority of...
no, you would just compute what's the fraction of your residues in helix, what's the fraction in beta strand, what's the fraction other.
Okay, alright.
I mean, you could have more secondary structure states, but in principle that... So I would argue for those 3. What I showed you before was 3 states.
Size.
Size. Length. Length is an issue. So we code that typically with 4 units in our group. And that is simply because proteins can be between 30 and 30,000 residues long. So if you just take this number and use a fraction of 30,000 as an input, then most proteins have a meaningless input here. So the way we do that typically is we have one unit that codes for longer than 500, one for longer than 250, and one longer than 125, and one for 60. That's sort of the domain, it reflects the domain organization. And it says that if the protein is longer than 500, well, it's a long protein, full stop. Where exactly you put these numbers, I'm not even sure that this is exactly what we used in the latest version. In the earliest version I used something slightly different, but that's the ballpark idea for these 4 units. And then you sort of fill them up according to what fraction in the interval you are in. That could be length. What else?
Amino acids on the surface.
The surface composition? Exactly. Any other idea?
You could use the actual amino acids in a certain part of the protein, like the first 20 or something.
And then what?
What? I mean,
And then what do you do? So you
Just-
slide through, And then the protein can be nuclear there, and then it can be cytoplasmic, and then it can be nuclear, and then you average?
It can be a peak, like single peptides that are at the beginning of a protein, so it might be that a certain region of the protein is relevant for the prediction, and you use the actual amino acid first.
So now you want to essentially look at the composition of the first 50 residues or something like that. Is that what you mean?
Could also be the order of them. So.
Of begin. So what did you mean by order?
That it's not only that don't have like 20 values, but I have 20 times 20.
Okay. So let's begin to discuss something else before we get deeper into this. Now, machine learning is really we're going to have most of the discussion next Tuesday, because we're going to have an early end today. So what we're going to begin with next time is an idea about the number of free parameters that we can have. Machine learning is full of rules, and most of these rules are not easy, don't typically apply. But one of the rules, and again I'm going to have a little bit more on that on Tuesday, one of the rules that people typically have is that the number of samples you have should at least be ballpark 10 times higher than the number of free parameters. Okay? Number of free parameters that we have here is typically input times number of hidden units. Now, if you have hidden units up to 10, must be a relatively simple problem. Say 20, there begins to appear some more complex distinctions. But let's just stay on the 10. We have 10 input units, and so let's stay on your 20 by 20, 400. 400 times 20 is 8,000. So now we have a classification of extracellular versus other. What we need now is 40,000 proteins for the classification of extracellular versus other. What we not need is 40,000 both together, but what we need 40,000 for typically is the smaller of the two classes, which means in this particular case extracellular. We don't have that. Actually, the extracellular proteins are in the ballpark of less than 5,000. So this number clearly is too high.
But how would you then learn such a sequence logo, for example? I mean, it's 20 positions, and you care for the actual order of the amino acids, not only the fraction.
The answer is not through this device. So you would essentially, now you're getting back into the cyclic peptide prediction. So now this is exactly what I said. There is sort of a machine learning device that does motif detection, and then you would essentially train a device to do motif detection that will not do de novo for everything. Maybe you could inherit that from the signal P. So then you could sort of take signal P and say, signal P yes or no, or something like that. And then you boil it down to 2 units, one unit, yes or no, whatever way of coding you have for that. So you have another device, and that other device solves a subtask, and that subtask is used as an important input. That's the way you would do it.